Welcome back to the Chem OG. Today we're going to talk about a very important topic when it comes to chemistry, and that is acids and bases. And we're not going to talk about all things acid and base. We're actually going to scratch the surface, and we're going to discuss how to measure the strength of an acid or the strength of a base. But before we do so, let's make sure that we cover our definitions. And so what's an acid? Well, an acid, one of the definitions is that it's something that produces protons, or if we're looking at this in water, it's something that produces hydronium in solution. Because as soon as that H plus hits water, essentially that oxygen in water is going to be attracted to it, and that's going to become H3O+. So it's something that produces either protons or hydronium in a solution, and those are known as the Bronsted-Lowry and also the Arrhenius definition of an acid. Or if we take a look at the Lewis definition of an acid, it's something that can pick up an electron. Okay, so it's an electron acceptor, and that also means that it can pick up, an electron from hydroxide. So it's something that can neutralize hydroxide as well. And what acids do is that they decrease the pH of a solution. So whatever pH we're at, if you add acid to it, it's going to make the pH of the solution go down. Now, bases are sort of the opposites in many different ways. So bases, instead of neutralizing hydroxide, they're the ones that actually produce hydroxide, and they actually are electron providers. So that's the Lewis definition of a base, and it's also the Arrhenius definition of a base in terms of Lewis and Arrhenius electrons and hydroxide respectively. Bases can neutralize any protons or hydronium that are lying around a solution, and as such, instead of decreasing the pH, they actually work to increase the pH instead. All right, so that's what we're looking at in terms of an acid and a base. Now, how do we determine when we have a strong acid or a strong base? Like, what does it mean to be a strong acid or a strong base? Well, the strength moniker has to do with how reactive the acid or the base is. So strong acids and strong bases are reactive and they're very unstable. Okay, so what does a strong species do? Well, a strong species, what it does is it makes products really readily. And so the way that we measure the product to reactant ratio is we take a look at something called an equilibrium constant. And when we're talking about an acid and when we're talking about a base, it's either a Ka when we're talking about an acid or a Kb when we're talking about a base. And so if you take a look at the way the equilibrium constants are set up, you'll notice that in each case, if you have a strong acid or a strong base, you're going to end up with a K value that is bigger than 1. So if I take a look at a strong acid like HBr, okay, or if I take a look at a strong base like potassium hydroxide, hydrobromic acid produces products readily. That's why this reaction arrow is a one-way street. It goes from left to right, and there's no going back. And so it produces protons and bromides readily. Potassium hydroxide, also one direction arrow, produces potassium, produces hydroxide. There's no back reaction at all. So the Ka for HBr is going to be rather high. And the reason for that is when we put our HBr in solution, it's going to be protons and bromides all day, every day. There's really not going to be much HBr at all. And in fact, for many intents and purposes, this number here down here is going to be a 0. And these numbers here are pretty large, relatively speaking. And so that means the Ka value is going to be a lot bigger than 1. And I can say the same thing about potassium hydroxide. So we're going to have a K plus and an OH amount that is way higher than the actual KOH that gets left behind. There's practically none of this molecule, and so this denominator here is really small. These numbers here are much, much larger, and that makes the KB, much bigger than 1. So when we talk about a strong acid or a strong base, really we use 1 as a benchmark value. If our equilibrium constants are greater than 1, then that means that we have a strong acid or base. Well, what if things are flipped? And let's say that you have something that doesn't dissociate readily and it leaves a lot of reactant behind. Well, what we call that is a weak acid or base instead. So weak acids and bases, they're not as reactive. And a better or more positive spin on that is that these molecules are a lot more stable. Okay, so certainly one way to think of a weak acid or a weak base is to think of a stable molecule. It doesn't really change that much. And so weak species, they don't produce products. They like to stay as reactants. And so that means we're going to have a Ka or a Kb value that's less than 1. So to give you an example of each, let's say we're looking at formic acid. So when we're looking at formic acid, it's going to produce a proton and its conjugate base, formate, but this reaction arrow is reversible. In fact, there's very little moving forward. There's quite a bit of back reaction. Instead, if I take a look at ammonia, when I put ammonia in water, it produces ammonium and it produces hydroxide, but not to a great degree. Okay, so I'm going to produce some of these products, but there's going to be a lot of ammonia molecules that get left behind that don't really react with the water at all. So when I take a look at the Ka and the Kb expressions for both formic acid and for ammonia respectively, I'm going to end up with a considerable amount of reactant in each of these cases. So a bunch of formic acid is going to get left behind. A bunch of ammonia is going to get left behind. And so these Ka and Kb values are going to be less than 1. And that is the hallmark of a weak acid and a weak base. So if we have these reactions happening in water, water has rules. And the rules for water are the following, is that the amount of hydronium and the amount of hydroxide, when I multiply them by each other, they need to equal a constant. And that constant is 10 to the negative 14 if we're looking at 25 degrees Celsius. Okay, so the amount of hydroxide and the amount of hydronium has to be level at 10 to the negative 14. Well, whenever you have two numbers that multiply together to equal a constant, it means that they have an inverse relationship. So as one goes up, the other one must go down and vice versa. And so if I check out what ammonium does in water, right, NH4+, what it does in water is it can act as an acid. It can give off H3O+ and NH3. There's also a good amount of back reaction that can happen here. And if I take a look at NH3, its conjugate base, we already mentioned that it produces ammonium and hydroxide in water. So if I take a look at the Ka for NH4+, and I take a look at the Kb for NH3, that's how those expressions look like. So anytime you take a look at a Ka expression in water, H3O+ is going to be one of your products. Anytime you take a look at a Kb reaction in water, hydroxide is going to be one of your products. Well, what happens if I decide to multiply Ka times Kb? Right? If I want to take a look at the relationship between the Ka for an acid and the Kb for its conjugate base, if I multiply those two numbers together, those two expressions together, what am I going to get? Well, Ka times Kb, let's see, there's an NH4+ and an NH4+ that are going to cancel out. And there's also an NH3 and an NH3 that are going to cancel out as well. And so anytime you multiply Ka times Kb for any acid and base conjugate pair, those two species are going to cancel out. And the only thing with which you're going to be left is the hydronium and the hydroxide. So anytime you multiply Ka times Kb for any acid-base conjugate pair, that's going to equal 10 to the negative 14 if we're doing this at 25 degrees Celsius. Okay, so once again, Ka times Kb for any acid-base conjugate pair is going to be equal to 10 to the negative 14. And so because that product is a constant, Ka times Kb is going to equal a constant, regardless of what temperature we're looking at. That means that those two numbers have an inverse relationship. As one goes up, the other one has to go down. So as an acid or a base becomes stronger, its conjugate base or acid becomes weaker. So there's that inverse strength relationship going. So let's take a look at a quick example. So let's say that we're taking a look at the numbers for that NH3 molecule that we were discussing earlier. The Kb for NH3 at 25 degrees happens to be 1.8 times 10 to the negative 5. So if I take a look at the Ka for NH4+, that's going to be 10 to the negative 14 divided by this number. And that happens to equal 5.6 times 10 to the negative 10. So if I take a look at this number here, and if I take a look at this number here, remember we said that anytime we have a strong acid or base, it should have a K value greater than 1. So if I take a look at that top number, and I take a look at this bottom number here, neither of those is greater than 1, which means, because both these numbers are less than 1, it means that NH3 and NH4+ are weak species. Each of those happens to be a weak base or acid. So this is something important that I want to emphasize, that when I have a weak acid, its conjugate is actually a weak base, as you can see from these numbers. Okay, so lots of students make the mistake, or sometimes you get taught incorrectly, that the conjugate of a weak acid is a strong base, or vice versa. That's not true, as you can see from these numbers, right? Anytime you have a weak base, its conjugate is going to be a weak acid. They do have inverse strengths, but they're both weak because they both have equilibrium constants that are less than 1. And so to kind of summarize our lesson today, the Ka times the Kb is equal to 10 to the negative 14 anytime you have an acid-base conjugate pair. And if you take the negative log of both sides, you'll find that the pKa for the acid plus the pKb for the base is equal to 14. So that only works whenever you have an acid-base conjugate pair. Acids and their conjugate bases have inverse strengths, and the conjugate of a weak acid is another weak base. If you happen to have a strong acid, its base is so weak that it essentially is very, very stable and doesn't really react too much. Okay, and so another way to think about a stable base or a stable acid is that it doesn't change the pH of the solution. Thank you so much for attending today's lesson. Please be sure to support this channel by subscribing and hitting that like button.